students.
I don't know my voice. He was all about.
So solution, I usually abbreviate that SOLN, and a solution is a homogeneous mixture. What do I mean by homogeneous? Looks the same throughout. It is going to be a mixture, so it's not a pure substance, but it's going to look the same throughout. So it's a homogeneous mixture. It's going to be clear, not cloudy, meaning we can see through it. And it can be of gases and liquids. Now we can have a solid solute, but eventually we're going to end up with just something that's either a gas or a liquid. Now air is a homogeneous mixture. It's technically a solution. Can you see through air? Yeah, and it's a mixture of gases, okay? And so even though we typically stay with this liquid, this aqueous solution, and we could also put AQ there. AQ means dissolved in water, okay? Gases can't actually have that same property, okay? The solvent is the dissolver, okay? Looks really fuzzy. There we go. And so this is usually going to be that liquid or the major gas that we see. So for air, that would be nitrogen gas. That's the majority of what air is. It's like 70-some% nitrogen gas. And for us, mostly in chemistry, this would be our water, our H2O, which makes it an aqueous solution. So our solute is going to be the chemical dissolved. So it's not the dissolver, it is what is being dissolved. We can see this diagram here, but most of the time we're not going to have a diagram that we look at. We're going to look at a chemical like iron 3 chloride. It's going to usually have an AQ after it. And so why did I possibly choose red for my iron 3 chloride? What do you remember about iron? It's like the brownish red. And so this chemical right here, that is the solute. It gives the color to the solution. It is going to be the solute, what we dissolve. When we look at concentration, it's what we're looking for the concentration of. This part right here is going to tell me the solvent, and that in this case, it is water, because I've dissolved it in water. And so what do we call this whole thing here? The solution. Now, we have 4 different ways that we can talk about our solutions, and they're going to deal with the amount of solute we have in them. And the first one is going to be an unsaturated solution. We're going to have a saturated. It was cold originally, so it's a little bit. I could have been smart and said all around you, because you're breathing it in. But I wasn't, so, I mean, I didn't really say that, I just told you I was going to say it. All right, so as we're going to notice here, going from left to right, it's the amount of solute we're going to add. So like a little bit, we've got more, and more, okay? Are any of those terms, do you recognize any of them? Saturated and precipitate. Okay, let's talk about precipitate first. What do you know about precipitate? It's going to be cloudy. We're going to have a solid being produced here, okay? And so when we talk about it in terms of our solution, it's where we've added so much of our solute that I can't get any more to dissolve, and it's going to precipitate out, okay? So we're going to see solid at the bottom, okay? We could put on here too much solute. We got too much solute there. And it's not that some of it didn't dissolve, it's just that I have so much of it that it can't dissolve anymore. You know, I was just about to mention that one because Cabriana talked about that last period. She's like, it's like when you put too much sugar in your cereal and you have cereal or sugar down at the bottom, right? Exactly. It's not all going to dissolve, okay? We can get it to dissolve, and some of that sugar actually dissolved a little bit, but we've got too much, okay? I liken it to sweet tea because I'm a northerner and we don't, stereotypically, we don't have sweet tea. We do now because y'all have been generous enough to send it up north so that we know what it's like, okay? But typically what you would do is you'd go to the restaurant, and if you wanted sweet tea, you'd order sweet tea. They come with a glass of unsweet tea and 2 packs of sugar. And you pour it in. Well, is all that sugar going to dissolve? It's not. Okay, but that's what they would do. That's northern sweet tea, okay? Except now McDonald's has sweet tea, and we have McAllister's up north, and so like it's just wonderful. Except I don't like sweet tea, so it doesn't really help me. But anyway, this would be like northern sweet tea, where we try to get sugar to dissolve. Some of it does dissolve, but not nearly enough because it's going to sit at the bottom. Or like Kiki was saying, it's like the sugar in our cereal. Or was that Kelsey? I'm sorry, Kelsey. It was Kelsey that said that about the sugar at the bottom of the cereal, okay? Some of it dissolves, but I've maxed out. I can't get any more to dissolve, and so the rest of it's just going to sit at the bottom. Now, you guys said you knew something about saturated. What do you know about saturated?
It's wet. Like when we saturate your chemical product.
It's wet, okay? It's absorbed. It's all in there. Can we get any more? No. We have maxed out on the amount of hair product that you can put on there, right? Because if you put any more, it's just going to drip off, okay? I like to think of this as that point right before on the northern sweet tea, before it starts sitting at the bottom. Or if you're dealing with the sugar in your cereal, you put just enough that it dissolves, but the moment you add just a little bit more, it's going to sit at the bottom, okay? So this is going to be the max amount of solute dissolved. I can't get any more in there. Now, if we think of it like a sponge, okay, like I tend to think of it like a sponge too. Like if I have a saturated, that sponge has all the water in it that it can get, okay? And we all know what that kind of feels like if you're doing dishes and stuff, but it's not dripping, There's no dripping out because if it were dripping, it would be like the precipitate. So we're not dripping out, but I can't put any more water in that sponge. It is full, okay? So that would be saturated. You may be familiar with saturated when we talk about saturated and unsaturated fats. Saturated means full, and for a saturated fat, it's full of hydrogen. Unsaturated means that there's more room for hydrogens to attach, okay? So unsaturated, is it full? No. So there's room for more solute. All right, so there's room for more chemical to be put in, maybe more sugar in our cereal before it becomes maxed out and we precipitate out, but there's room for more there, okay? If you're thinking of the sponge, it's just barely wet and I can put more water on it, okay? What would supersaturated mean? Overfilled, right? Okay, too much. Well, here we're gonna have, and I like to say extra, because overfill kind of makes it sound like a negative thing, okay? But I have extra solute dissolved. Whoa. What does that mean? If I have too much, it precipitates out. Okay, so this is all dealing with northern sweet tea. How do southerners make their sweet tea? Extra sugar, right? And you heat it up, right? You heat it up. And because you heat it up, you can get more sugar in there. If we took our cereal, now I know that this would not be yummy cereal, but if we took that cereal that had the milk and the sugar at the bottom and heated up that milk, could we get more sugar dissolved? Yeah. So to get this supersaturated solution, what we do is we take this precipitated solution and increase the heat so that we can dissolve the rest of that and it stays in a solution. Sweet tea, southern sweet tea, is a great way to think about it because we are making what's called a simple syrup. We're making a whole lot, it's usually a cup of water to a cup of sugar. And it won't all dissolve to begin with. But when you heat it up, you can boil it, and when we do that, we can make it into a supersaturated solution, which means we've just dissolved a whole lot of extra sugar to go in that sweet tea, okay? It stays dissolved, okay? So we've just almost expanded how much water our sponge can hold or how much solute our solution can make. Now, these can be a little temperamental, because if you get some crystals forming, like if you're making candy, it'll crystallize real quick, okay? Kind of like with our borax, okay? We tried to do a supersaturated solution and then we let it crystallize. Okay, do you remember our borax one? Okay. So that's supersaturated. All right, we've got some formulas we need to talk about today. One of them is molarity. Have we talked about molarity before? Don't think too hard. With molar mass, it's not necessarily molar mass though. I gave you a hint with don't think too hard. It's your concentration. That capital M is molarity. And so our unit here for molarity is concentration moles, or molarity, we say molar. And it has a formula, and we put the brackets, and that's going to be around our solute. And I'm going to keep on color coding, you don't have to. But solute, actually, I lied. It's still going to be solute in there. I'm just doing the wrong color. So we normally put the chemical in there, like we did up here, FeCl3 would be our solute, but it's the concentration of the whole solution, and that would be equal to the moles of our solute. N means number of moles over our volume in liters of our solution. Where have we used this before? Molar conversions, right? So we've got factor label. We use it for stoichiometry. We can use it for what's called titrations and dilutions. I love how I got rid of my drink and now I'm getting a tickle in my throat. All right, so we have this. This is a fraction, isn't it? Which means it's a ratio. We're just not multiplying by 100, but it's still a ratio, and we can use it as a conversion factor. Another one that we have is called molality. We read it molal, and I use a script M for that. It is different than a capital M. It is not meters. It is not mass. But our molality is going to be equal to the moles of our solute over the kilograms of our solvent. This is great for something called colligative properties. Which Friday's lab is going to deal with. We also have one called percent by mass. What would the unit be for a percent? Exactly. And so for percent by mass, we would have the percent of the part equal to the mass of the part divided by the mass of the whole thing times 100. Wait, haven't we done that formula before where it's part over whole? So this is used a lot for empirical and molecular formulas. Now, mole fraction, I'm skipping to the bottom. The mole fraction does not have a unit because it's just a fraction. But we're going to use a script X, and that's going to equal the moles of the part over moles of the whole thing. Wait, that seems really familiar, right? Instead of mass of part over mass of whole, we have moles of part over moles of whole. And this is used for Raoult's law. In gases. Now, I skipped over percent by volume. We don't normally use percent by volume anymore, but it would still just be a part over a whole. For real. Sorry, we got a long way to go. All right, let's take a look here. We're going to go down here to E2. problems. Well, molarity, our concentration of our solute, is equal to moles over liters. That's moles of our solute over liters of our solution. Just reminding this is our concentration moles. In the middle. Sorry. And so on E2, it wants us to determine the mass of ammonium nitrate to make 50 milliliters of 0.24 molar solution. What is your gut telling you to do? Change milliliters to liters, underline and circle. Let's start off with underlining and circling. What are we looking for? Mass of ammonium nitrate, and I really should have circled in red, sorry. So I'm looking for grams of ammonium nitrate. Our formula for ammonium nitrate would be NH4 with a plus charge and NO3 with a -1 charge. So when we crisscross, we get NH4 and O3. Well, what am I given? 50 milliliters of a 0.24 molar solution. So I heard convert milliliters to liters. How could we do that? Times 10 to the -3rd, or move your decimal point back 3 spots, okay? I'm going to start off with that 50 milliliters to show you how this really isn't new. What would I have to do on the bottom? 1 milliliter to 1 times 10 to the -3rd liters. Excuse me, y'all. All right, where would I go from liters? Ooh, concentration mole, because I have this capital N, right? That means moles per liter. Now, technically, when I do this, it switches from the solution to the solute, to just the chemical. So down here that involves the water, down up here that's just the chemical, the solute. And then from moles, do I need to go from mole to mole? Am I asked about the same chemical? Yes. So I don't need to do mole to mole. And so now I can do moles to grams. How would I go from moles to grams? Molar mass. So let's figure out what our molar mass is of ammonium nitrate. That was too much. Okay. Good. I'm getting 80.06. I heard today to get 80.06. Okay, and so now we can go ahead and calculate it. Because I'm teaching you today. That's why this class is going. This is going by fast?
No, it used to go like that.
You guys are just ready to be done. Is what it
Can
is.
we just be ready to be done? Can we be done?
Can't be done. I can't help it if you're ready to be done, but we can't be done. We do still technically have close to a month left of school, so.
We get out on the 23rd, though. Y'all get out on the 23rd.
I get out on the 24th.
But the students get out on the 23rd.
Alright, when they start to agree. Again.
When the grades freeze for the report cards for these
20th and 23rd.
Hey.
Oh, that's a win.
They do good, man. They got them good.
Exams start on the
You be exempt from exam.
20th.
You can't be exempt from the exam.
You can, if you have an A.
They just not never give us an exam though. They're supposed to.
I give an exam though.
Can you not give it a exam?
Yours is the 20th and 21st. So yours is the 21st.
You got 2 days more for exam.
20th is 1, 3, 5, 7.
Oh.
21st is 2, 4, 6,
They
7.
doing the mug.
I'm videotaping, or I would comment on that. All right, so are we getting 0.96 grams? Is this really any different than what we've already done with factor label? Mm-mm. Let's look at E3. On E3, we're looking for a concentration, right? Now, concentration is that capital M. And that capital M means moles over liters, right? So I'm going to look for moles on top and liters on the bottom. That is something different. We've always had just one unit that we've looked for, and it's always been on the top, okay? So this is going to look slightly different. I'll show you a couple ways that we can approach it, okay? But I'm going to have to start out with the 2.98 grams of sodium chloride. Sodium chloride is NaCl. Where would I go from here? Is it 1 gram on the bottom? It's the molar mass. I just remembered it from last period. Now, I've got moles on top, right? Didn't we want moles on top? Okay, so I can stop here because I wanted moles on top. So I need to have liters on the bottom, right? But I don't want to take mole diagonal, do I? So I'm going to put liters on the bottom somewhere. I could do it at the very end if I wanted to. I could put it here if I wanted to. Because I'm still going to multiply across the top and divide by the bottom, right? Or I could stop here, get an answer. And I'm going to show you both ways what it would look like, okay? So I have moles of NaCl, and then I know that the concentration of NaCl should equal our moles over liters. Well, 0.0510 moles over 0.789 liters. And we're still dividing by our liters, right? And I'm getting 0.0646 molar NaCl. So I'm going to show you real quick what it could look like alternate ways. So this is one way that students like to do it. So sometimes students will do it this way where they realize, ooh, I've got moles on top. I need to put it over liters. So let me just put a liters down at the bottom. Putting nothing on top. You could do that. You could also say 2.98 grams NaCl. And instead of having nothing underneath here, you could go ahead and put your 0.789 liters here. Okay? Are you still going to end up with the exact same answers? So if you don't like having this blank spot up here, or if you don't like putting that underneath the first number, you can always stop at mole and then divide it by hand, like we did here. So weigh 1, weigh 2, and weigh 3. And they are all valid ways of doing it. You're all going to end up with 0.0646. So whatever floats your boat, okay? Okay? So either way, all right? It's not time to go.